Okay, so it seems like we're ready for you.
Right. Good morning, all. Nice to see you all. Friday again. Where did the week go? We're going to be doing some electronics. Oh, but not electricity again, you say. But we might do electricity about 5 times more till everyone gets it. But we're going to try something slightly different today. Today, we're going to talk about electronics. I'm just wondering whether we should get someone to volunteer to come to the front and answer the questions. Mustafa and Matthew did such good jobs. Is there maybe someone else who feels like volunteering? Because I think we're going to have an interactive session today. So maybe if you could think about it, otherwise I'll just have to lecture. But either way, I'm sure we'll survive. Okay, we're going to talk a little bit about electronics and semiconductors. Now you're going to say, some of you I know are going to say, but sir, transistors and LEDs are not in the syllabus. And my response is, what century, folks, are we living in? We're living in, was it the 21st century? And how come LEDs and transistors and semiconductors and things like that are not in the syllabus? But consider it, it's just another way of trying to teach people electricity, which people notoriously struggle with. Now, the Chinese are busy building robots, and those robots are building more robots. And I don't know if you've seen some of those Chinese factories, or even Elon Musk's Tesla factory. Almost everything in Elon Musk's Tesla factory is built by robots, and robots are electronics. So tell me, why is it that we are not teaching you robotics and electronics at school? So I was hoping this year to teach you, some robotics, but then the pandemic occurred, and all the components that I'd ordered from AliExpress from China, about 4 of them arrived, and then the rest got stuck in our post office somewhere. But I was hoping that we could do a little bit of robotics and electronics. But anyway, today I'm just going to do a little introduction to robotics and electronics, and teach you electricity, which is definitely part of the syllabus. Okay, so I'm self-taught in electronics, and you know what I know about electronics is dangerous. But just let me show you what you can do with electronics. I don't know if you can see there's a light above my blackboard. Okay, I seem to have hung up. Let me just go click here. Now, I can switch that light on and off by pressing this TV remote. So if I press this lower button, it goes off. I press it again, it goes on, off, on. So that was just like some little electronic circuit that we made. It reads my TV remote, and then it switches that strip of 12-volt LEDs above my blackboard on and off. And it's very nice. You can lie in bed and just switch the lights off from there. You don't have to get up and switch them off. So there's a lot you can do with electronics. Look, eventually, China will just lead the world in robotics. And they won't have people in the factories will be working day and night churning out 5G phones, computers, cars, and they will take a lot of the jobs. So I think that it behooves all of us to know something about electronics. I mean, don't you want to be making those robots that are churning out stuff and getting the profits from it? And if the Chinese are the only ones doing it and the rest of the world falls behind, like South Africa, then we'll be, for the rest of our life, condemned to buying Chinese goods instead of making them ourselves. And then they'll be the people getting rich and we'll be having, So definitely robotics is something that we should think of. Okay, so I've got a little circuit here. I think you know what this is. It's a set of batteries. And then it goes up to there is, I think you may know what that is. That's a resistor. And then here is something that you haven't seen very often. It's so tiny, it's hard to show you, but it's a transistor. It's got 3 little legs, 1, 2, 3. And then it goes to an LED. And then it comes back. So there's a closed circuit. Okay. And then what does the transistor do? Well, it acts like a little switch. So let's just show you. I'm just licking my fingers and I'm going to touch the middle lead and you see the light comes on. You see the LED comes on. My fingers are closing the circuit. I hope everyone can see that. So that's one thing that you can do with a transistor. If you touch from the positive side of the battery to what they call is the base of the transistor, if you bias the base of the transistor positive, it will come on. Now, if I take the base, again, I'm licking my fingers and I try and touch it to the negative side of it, nothing happens. But if I take it and I make the base slightly positive, that the LED comes on. So already you could see this could be quite useful. Just depending what you put between here and here, you can get your LED to glow. So let's just draw the circuit as we would if it were an electric circuit. So here is our battery. We've got 4 batteries, so let's draw another one. 1, 2, 3, 4. There's the positive. What does the battery do? It raises the voltage to plus 5 volts. This side is 0 volts. This side goes to a resistor. The resistor goes to a transistor. How does a transistor look like? What is its symbol? I'm sorry, let's just draw it correctly. And then this goes to an LED. And then that closes the circuit. And we call this your collector. We call this your base. And we call this here with the arrow, it's got a little arrow, that is called your emitter. I just hope I'm spelling emitter correctly. Has emitter got 2 M's or 1? But anyway, it's your emitter. Maybe it's 2 M's and 1 T. Let's try that. I don't know. Which one looks more correct? Anyway, emitter. Someone can correct me. This is a science lesson, not an English lesson. Now, let's just see. Do we have any volunteers to sit at the front and answer questions or not? Okay. Otherwise, then maybe I'll just ask a few hands. Tell me, does that circuit look like a closed circuit to you? Does it look like a closed circuit to you? Yay, thank you. Who do we have today? Is that you, Mustafa?
Yes.
Thank you so much. I greatly appreciate it.
I know.
Okay, guys, is that a closed circuit as it stands?
So like one, see? No,
Is that a closed circuit?
no,
Okay, what is a closed circuit? A closed circuit is one in which a current can flow, right?
yes.
So can anyone tell me why that is not flowing, why a current is not flowing? It looks like it's closed. I mean, here's the current. It's going to come from the positive. It's the resistor's not going to stop it. And there's your light emitting diode. So why is your light emitting diode not glowing?
I don't know, so they told me to say no.
Okay, fantastic. You're doing a fantastic job. Okay, this is why it's not glowing. A transistor acts like a switch. That is a transistor. A transistor can be open or a transistor can be closed. So what determines whether a transistor is open or closed? Now, I gave you a hint. I said to you that the transistor has got 3 wires. Wire number 1, which is your collector. Wire number 2, which is your base. And wire number 3, which is your emitter. Collector, base, emitter. And I said, if you take your fingers, here's my big fat finger, and here's my thumb. Okay, I've got a few more fingers. And I lick my fingers, and I touch between there and there. It is like adding another resistor. And then when I touch between there and there, the base becomes slightly positive. And then your LED gives off light. Now, when that occurs, Mustafa asked them, is that now a closed circuit?
Azra said yes.
Okay, so it's a closed circuit. So we call this type of transistor.
I need to put them in the mic. Oh. It wasn't me.
We call this an Npn transistor. Now you get other types of transistors that are called Pnp transistors. The important part about this is this middle letter there. The middle stands for the base. And if the base is P or positive, then this acts like a closed switch and a current flows. All happy with that? Mustafa, ask them if they're happy with that.
Yes, they're happy.
Okay, I'm so happy they're happy because when they're happy, I'm happy. Now, Mustafa asked them what will happen if I take my fat hand again. There's my hand, and I put my fingers like this. And this side here is the negative side of the battery. That's the positive side of the battery. And I bias, my hand acts like a big resistor. And I bias the base negative. Ask them, do you think the LED will glow?
No.
No. Why? Because this type of transistor must have the base positive in order that this switch closes and then a current flows. Okay, so now we could ask ourselves, what possible uses could this circuit have? Because, you know, my dream would be this, that of all of you who are watching today, some of you will go out. Do you know how much these things cost? They cost to make a few cents. To buy, they probably about R1 each. These resistors, let me show you my collection of resistors. These resistors, here's my collection of resistors. These are 0 to 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 100, 200, 300, 400, 500, 600, 700, 800, 900 ohm resistors, 1,000, 2,000, 3,000, 4,000, 5,000 ohm resistors, 10,000, 20, 30, 40, 50, 60, 100,000. Then we go into the many thousands of resistors. Okay, but these resistors cost like a cent or two each. So don't think because I've got a collection of resistors, this is only some of the resistors, but just with a few cents worth of electronic components. Here's your LED, that probably costs about R1 or two. So all in all, this whole circuit costs you, let's say, R5. The batteries are the most expensive thing. Okay, so let's suppose we want to go crazy. Like, I sometimes want to know when it's raining so I can run out and catch rainwater. Okay, especially when Cape Town was in a drought. So what do? We take this. We take a little lid. We place this lid outside. Okay, Mustafa, this little lid is outside. It's in the outside in the sun. Here's a tree. Now ask the class, what do you think that circuit's going to do? What does that circuit do?
What does it do? Apparently, it does nothing because they're not giving me an answer. So.
Okay, first of all, as it stands there, you're right. It does nothing. Because is the circuit closed?
No.
No. Okay, now what happens when it rains? Okay, watch what happens. Big fat drops fall in here. And eventually we got water there. I know you can't see. Let me just show that. Okay, so it rains. Raindrops fall. This is a lid. This gets filled with water. So now the circuit can go like that. So ask them, Mustafa, what use has this circuit got?
Apparently, it doesn't have a use, sir, because no one's giving me an answer.
Okay, but Mustafa, you're a genius by yourself.
Like
What do you think I would set up a circuit like that catches rainfall, and then what would happen when that lid fills with a few drops of rain?
You have rain.
Okay, would the light go on when it rains?
Yes, yes. Oh, there's a light.
Okay, so the LED would go on when it rains. And that would be able to warn me, because sometimes it rains and you don't know it. And then when the LED comes on, you know that it's rained. So at night, you will know when it rains. Or you can do this. You can put a little buzzer instead of an LED. You put a little buzzer there. And now you're asleep at 2 o'clock in the morning. So I put a little buzzer instead of an LED there. At 2 o'clock in the morning, it rains, and your buzzer starts buzzing. You like that?
Yes.
Okay, so there's a use for just one transistor. It's a rain detecting circuit. I want to show you if I can find where I put it. Okay. I hope you can see this is a little round thing with two legs. It's called a photoresistor. Okay, photoresistor. It's a little thing with two little legs. What if I put that here? Now, a photoresistor, its symbol is this. Now, what happens is when light falls on it, it conducts a current. But when light doesn't fall on it, it doesn't conduct a current. Okay, so it's a photoresistor. Mustafa, just ask them. They must listen again. When light falls on it, it allows a current to flow. So what do you think this circuit will be useful for?
Solar panels.
Okay, so say it's light. Say light shines on it. Will this glow or won't it glow?
That will glow.
Yeah, when light falls on it, the LED will glow. Now, just ask them if that makes sense to everybody.
Yes.
Okay, but that's not a very useful circuit. But let's suppose we wanted, when it turns dark, we want the light to come on. So this is what we could possibly do. Let's put the photoresistor where? Let's put it here. And let's put another resistor here. That's about equal. So this one is equal to that one. Now we're beginning to see why we have resistors in parallel and in series. Now, just have a look at that circuit. These are two resistors of about equal. We say that resistors in series are voltage dividers. Resistors in series are voltage dividers. Are these two resistors in series?
Aiden says yes.
Okay, Aiden's right. Now, are these two things in parallel? Is that in parallel with that?
Aiden says yes again.
Again, he's right. He's a genius. And let's just see. You see, let me tell you what what the problem with schools is. The school circuits are only resistors. There's nothing really more boring than circuits with just resistors. Look, I've already shown you how to make a rain meter. I've showed you how to make a thing that turns the light on under certain circumstances, and I'm about to show you how it turns the light on when it turns dark automatically. An automatic light turner oner. So I think, so why I'm doing this today is to show you that if you add a few components that are actually more interesting, you can do something useful. And now I hope that maybe you would start thinking about that electronics is actually some useful subject in the 21st century, because it certainly is. Okay, but we need to still know some of the basics of electricity. So let's go through some of the basics. So what do we have? You must be able to recognize this is in parallel with this. That's in series with that. That's in series with that. We have a parallel circuit and we have series circuits. Now, at school, they just give you parallel and series circuits, and they don't tell you, there's nothing interesting about them. They just ask you to calculate the resistance, for example. It's totally unimportant and worthless.
Yes.
It's just an exercise. But here it's important. Okay, so let's just go over some of our basics. I said to you that resistors in series are voltage dividers. Okay, this is a 6-volt battery. How do those two equal resistors divide the voltage?
Azra says in half.
Who says?
Azra.
She's also a genius. So the voltage here would be plus 3 volts because they divide it equally. Okay, now let's see if someone will be able to tell me. During the night, this resistor becomes much, much bigger because there's no light. And let's just draw this as a small resistor. I know it's not technically correct, but just to help you visualize it, you've got a small resistance, let's say 1 ohm there, and let's say you've got 10 ohms, or let's say, okay, this is 6 volts. Let's say this is 9 ohms. Does anyone know how the voltage would be divided now?
No.
Okay, well,
Nope.
let's add, what's the total resistance in this circuit? It's 9 ohms plus 1 ohm, right?
Yes.
So what's the total voltage, with the total resistance here?
10.
10. Now, do you guys know, where does the voltage fall the most? Over the big or the small resistance?
Azra says the big.
The bigger the resistance, the bigger the voltage drop. Exactly. So you would divide, if this is 10 ohms, you would divide the 6 volts by 10, which is 1/6 of a volt. So it would drop 1/6 of a volt here, and it would drop 9/6 of a volt here. So it would drop 9 times more. So tell me, has the voltage here risen above? What is the voltage here going to be equal to? It was 3 originally. Will it go up or will it come down?
Down.
Okay, so let's look at it logically. It's 6 volts, 6 volts, all 6 volts. 6 volts, 6 volts, 6 volts, 6 volts, 6 volts, 6 volts. It only drops a tiny bit here. So now it's, let's say, 5.9. Then it's going to drop the rest of it over the remainder. So the voltage here has risen. It's gone up. Because this has got no light shining on it, and therefore its resistance has gone up. So that way, we've raised the voltage. Does that make some sort of sense?
They say no, sir.
Okay, well, let's try again. Okay, I'm going to put 1, 2, 3, 4, 5, 6 equal resistors. Okay, 6, 1, 2, 3, 4, 5, 6 equal resistors. Okay, how much of the 6 volts will drop across resistor number 1? What will the voltage drop across here be? They're equal resistors.
Nobody's giving an answer, sir.
Okay, by the end of this lesson, you're going to be geniuses, so I'm not worried. Resistors in series of voltage dividers. There's 6 resistors to divide 6 volts by. So each resistor drops the voltage by 1 volt. So what is the voltage here going to be? 5 volts, 4 volts, 3 volts, 2 volts, 1 volt, 0 volts. If I had to put a voltmeter at all those places, that's the voltage I would get. Happy?
Yes.
How many are happy, Mustafa?
All of us.
Okay, well, let's see if we're still happy. Okay, what if I had to put, now remember this base must be positive for it to light up. If I put the base here, would this LED come on? Is it very positive?
Azra says no.
Ask her why she doesn't think 5 volts is quite positive.
She changed her mind.
Okay, ask her if I put it here, it'd be less positive, right? And then I could put it in varying places in between. And so this base is going to, here it's only 1 volt. Okay, so we could play around, but what I'm doing is I am physically moving this pointer to here. Okay, now because this is closer to the 0 volts, or the negative side of the battery, this base is very negative. And if I move it closer to the positive side of the battery, now it becomes very positive. So I can get any voltage I want on the base. Okay, let's just try them, Mustafa. Say I want to get a voltage of 3 volts on the base. Between which resistors must I place it? Where must I place it? Between resistor 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6.
Where must you place it?
Where must I place the base pointer?
Azra says on the one that's more positive.
Okay, so do you see that if I place it here, it's going to get 3 volts? Let's try that again. How will I get 4 volts? I place it there. How will I get my base to be 5 volts? I place it there. How will I get my base to go off? I will place it either there or there. Okay, just ask them if that makes sense.
Yes, it makes sense.
Okay. So, you see, you're seeing something that you've never seen before of resistors in series. And this is one of the most common in electronics uses of resistors in series. It's to get any voltage you want. If you have enough resistors in series, each one divides the total voltage by the number of resistors. So say you've got 6 volts divided by 6 resistors, each one will drop it by 1 volt. And so if you have enough resistors dividing the voltage, you can get any voltage you want. So now you've seen what's the use of resistors in series. Okay. Now tell me, why do I have this circuit and this circuit in parallel with each other? Any ideas?
No, none of us have ideas. So
Okay, let me ask this question. Does each of these branches have the same voltage across it?
I'm gonna say no.
This is 6 volts, 6 volts, 6 volts, all 6 volts, 6 volts, 6 volts, 6 volts, naught 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 volts. Do both streams have 6 volts across them?
No.
Okay, so where is the voltage dropping before it gets to the branches?
D.
Okay, I'll move it. You tell me, where is the voltage dropping? It's 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. Stop me where it changes. Is it still 6?
Yes.
6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. Is it still 6?
No.
Yeah.
Oh.
Is there any resistor to change it?
No.
So it's 6, right? Okay, let's go the other side. I wish I had colored chalk, but I don't. Naught, 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 naught. Hits a resistor. Is there any So is this whole bottom circuit naught?
Yes.
Okay, so you've got 6 on the top, naught at the bottom. The only time it changes is when it hits a resistor. So can anyone tell me why I bother to have 2 streams of parallel components?
Aiden said.
Why do I have 2 sets of parallel components?
To make it complicated.
It actually makes it simpler. How many battery boxes would I have to have if I didn't put them in parallel?
Azra says 2.
I'd have to have 2 battery boxes. So can I use the same battery box for both streams?
Aiden says no.
Ask Aiden why I can't use the same battery box for both.
Why, Aiden?
I am using the same battery box for both. But is there any objection to using the same battery box for both?
It doesn't seem like it, sir.
Okay, great. So that's the reason why we have things in parallel. So we don't have to have a separate battery box for each stream. Now, what is the purpose? What am I doing with this stream of resistors here? What am I using them to do? Am I using them for to somehow influence the second stream?
I'm just gonna say yes. Yes.
Yes, I'm using them to create a voltage on my base, a varying voltage on my base. Okay. Now, ask the class what the LED is for.
I'm gonna answer now.
Why do I bother to include an LED?
Huh? What? To see if there's electricity flowing.
Genius. Well done. Okay, so now we know the use of the LED. So, anyone tell me what's the use of the transistor? To act like a
switch.
Well done. So now we know that is to show if the switch is open or closed. We know that this base needs to have some connection to something to turn it on or off, and that's where we can vary it. Okay, so now the next question is, what do you think this resistor's use is? Why must we include that resistor?
To slow down the current.
Okay. Guys, never say slow down the current. I know people use it. It's to reduce the current. The current always flows at the same speed, whether it's a big or a slow current. I mean, whether it's a big or a small current, it always flows at the same speed. But it could be a big river flowing at the same speed or a little river. Okay, so here we come to a characteristic of LEDs and these two components. These two components are what we call non-ohmic components. Now, let me explain to you what non-ohmic means. Let's suppose I got rid of that and I just joined this here. And I attach this to the positive. Okay? Ask them, will a current now flow?
Will the current flow?
Will a current flow?
They don't know, sir.
Look, is the base attached to the positive or the negative? Follow it. What's it attached to? How many volts?
What's the answer? 8 and 6, yes.
Is it attached to, what's the voltage on the base?
Azra says 6 volts.
You're right. It's positive 6 volts. That's very positive. Will a current flow?
Yes.
Right. So now the transistor switches on and a current flows. And if you don't have that resistor, you'll get a nice little bright little poof, and this whole thing will burn out. This whole thing it won't melt, but it'll just burn out. So it'll be bright for about 1 second, and then it'll just burn out. This thing will burn out too. And if they just burn out, it's because they have no resistance. When they switch on completely. When they switch off completely. There's no half measures with these transistors and LEDs. They've got no resistance. Does that make sense?
Yes.
So now we sit with a circuit that's got virtually no resistance. So what happens is, what's the current going to be like in this circuit? It's a short circuit, right? I just want to show you a nice little site that I found. I just want to show you the site that does Ohm's law. Okay, you see volts equals amps times resistance. Here's a little circuit. It's got some batteries, it's got a current, and it's got a resistor. So what will happen to the current, which is sitting at 6.2 milliamps, if I crank down the resistance? Who could tell me what will happen to the current? Just ask them. I'm going to reduce this resistance. What will happen to the current?
The current will increase. So
okay, watch and see. This resistance is 512. Watch, I'm going to crank it down. I've reduced it to 57 ohms. Look, the current has increased. If I crank up the resistance, watch what happens. This is the current. That's the I. Okay, what happens if I increase the resistance? So increasing the resistance reduces the current to 4 milliamps. Decreasing the resistance to 10 increases the current to 470 milliamps, which is a half an amp, which is quite big. Okay, so to get back to our circuit on the board, when our transistors open, it's got no resistance. It's like I'm doing this. And then the current becomes ginormous, and then it melts and burns out the transistor and the LED. Just while we're here, what happens to the current if I crank up the voltage, keeping the resistance at 518? The greater the voltage, the
equal the current.
Okay, let's see if that's true. At the present, the current is 9 milliamps. Watch, I'm going to increase the voltage. As the voltage gets bigger, the current gets bigger. That's Ohm's law. As the voltage gets bigger, the current gets bigger. As the resistance gets bigger, the current gets smaller, keeping the voltage the same. We've always got to keep something the same. So if we keep the resistance the same, increasing the voltage increases the current. And then they don't allow us to change the current because it's these two that will change the current, the volts and the resistance. Okay, so I just want to stop presenting. And just, I want to show you something. Okay, I'm just going to get rid of this now. Now, you guys actually did an experiment or a practical on this. If I have volts here, current here, for a fixed resistor. Okay, who can tell me what that graph will look like? The classical graph of Ohm's law. What will the graph look like? The greater the voltage, the
Greater the current. That's what I see.
So what kind of graph must I draw?
A straight line.
A straight line directly proportional graph. And we call that an ohmic resistor. Okay, so believe it or not, this question comes up often in your exam. And that was what the prac was about. That's, you remember you drew a graph that looked like that when I gave you 4 resistors and you had to plot voltage against current. You got a graph that looks like that. And one plot or two might have been out of place, but it was a straight line graph. Okay, but what happens with LEDs and transistors? They're not ohmic resistors. This is how their graph looks. Okay, so I crank up the voltage. As the voltage increases, the current doesn't change. Now, how do I draw that? I guess it would look like this. As the voltage increases, the current doesn't change till it gets to a specific point, and then suddenly the current becomes enormous. And that's a non-ohmic resistor. Okay, I want to use an analogy. It's of ohmic and non-ohmic parents. Okay, let's suppose you got ohmic parents and you ask them at a young age, can I go out? And there's resistance. No, but I'll allow you to go out with your friends, but be home by 4 o'clock in the afternoon. Okay, then you get a little bit older, you show a bit of responsibility, you meet someone you like, can I go out? And your parents say to you, yeah, maybe, but you must stay at home, and they must leave at 8 o'clock. Okay, that's ohmic. They're kind of slowly increasing their resistance depending on the pressure that you give them. And then finally, when you're your age and you want to go out, they say, yeah, you can go out, but you must be home by 11 and you must call me every hour or something like that. Now, that would be ohmic parents. Now, let's give you an example of non-ohmic parents. I don't know if you've heard of the Amish. They're very strict with their children. The Amish ride around in buggies. They don't use electricity. They don't drink. They don't smoke. They don't gamble. They don't do anything. They just farm and use non-power tools. And their children are very strictly raised. So the children can ask them for, can I go to the shop? No. Can I date someone who's not Amish? No. Can I date an Amish boy? No. Everything's no till they reach age 18. And then suddenly they have some term called Rampfenstein or something. It's some German term. When the children at age 18, they're allowed to go crazy. You can go out, you can get drunk, you can do what the heck you like, you can travel, you can... they're not encouraging you to do this. Go and try and see if you like that lifestyle. So that would be like a non-ohmic parent. In other words, what happens is you increase the pressure, increase the pressure or voltage on the parent, and suddenly at a certain age, woof, everything is allowed. And then the hope is that you're going to hate it so much, being drunk and disorderly, and that you'll come back and become a good Amish member. I like the Amish a lot. Okay, but that would be a non-ohmic kind of parent. Okay, so there's your introduction to a little bit of electronics. Okay, can I ask you guys to take out your paper 1 and let's just work through some electricity problems. Now we've worked through 1 or 2. I know we've done 1 or 2 electricity problems, but not many. So I'm going to skip the first few. I don't know if we've done this 1.8, but let's just give it a go. 3 light bulbs X, Y, and Z with resistances R, 2R, and R, respectively, are connected in a circuit as shown below. The battery has negligible internal resistance. When switch S is closed, all the bulbs light up. Okay, so this bulb Y has got twice the resistance of the other 2. The reading on the ammeter is 2.5 amps. Which one of the following correctly describes the readings on the ammeters when bulb Z burns out? When that one burns out. Okay. Now, first of all, you've got 3 resistors in parallel. When this one disappears, will the total resistance of the circuit increase or decrease? Ask the class that if you don't mind, Mustafa. Will this A go up or down?
Will the A go up?
Will this total current go up or down?
Everybody looks confused, so.
I know. I could go to any school, ask the same question, and I'll get exactly the same look. So our question is, they say that when the switch is closed, the reading on ammeter A is 2.5. And then which one of the following correctly describes the readings? Will it does this one go up or go down when the bulbs burn out, or stay the same? Anyone got an answer?
Not at all.
Okay, and it's like I say, I'm hoping to make some impression on you, and there's a rule. Tell me, do resistors in parallel increase or decrease the resistance? The more resistors in parallel, the more or less the resistance?
Answer is more.
I said less.
They say less. They change it to less.
But do people agree with her?
I don't know.
So here's a rule that you've got to know. You've got to remember it. If you don't remember this rule, you're going to be screwed. The more resistors you add in parallel, the less the resistance. How can that be? Aren't resistors supposed to increase the resistance? Aren't resistors resisting?
Yes.
But that's only when they are in series. Now, here's the logical reason. You've got a river. It's flowing, flowing, flowing. It can choose this path, this path, this path. If we add a path, more water can flow. The more resistors we add in parallel, the more paths there are for water to flow, therefore the greater the current. Resistors are also conductors. People don't realize that resistors are conductors. We're adding more conductors. So therefore now, with that in mind, that when you add resistors in parallel, it adds more paths. It therefore reduces the resistance. What are we expecting to happen when this light conks out? We're expecting our resistance to increase because this is no longer a conductor. So the total resistance increase, the current will go down. So the answer is one of C or D. Everyone happy about that?
Yes.
It's one of C or D. Okay. Now here's the next question. If this has got twice the resistance of that, which they say it has got, why it says is twice the resistance of X, will more or less current flow through Y?
Less.
Less. So here we're going to get less current. Here we're going to get twice as much because it's twice, it's half the resistance. This is twice the resistance, therefore it's got half the current. So now we want an answer that's got this current is twice as big as that current. So now we look, A1 is 1, A2 is half that. They can't be equal because these are different resistances. So we know our answer is this must decrease and this must be twice as much as that. So the answer is definitely D. Okay, Mustafa, please ask them if they understand that.
Yeah. Yes, they understand it.
And guys, what you must please write a rule here. Write a rule. Next to it. Resistors in parallel reduce R total. Increase the current. Or I total. Okay. And then if you do that and you work through these and you make sure you know how you worked it out, now you will become experts as much as is possible on electricity. Okay, here you notice the questions are always 1.18. 3 identical light bulbs. 3 identical light bulbs are connected in a circuit as shown below. The resistance of the battery and connecting wires can be ignored. This is a difficult question. I'm almost feeling I should leave it and go on to something easier, but okay, we The reading on voltmeter 1 is Okay, which one of the following statements is correct when the switch is closed? So we close the switch. Voltmeter 1 is half that of voltmeter 2. So anybody got any ideas here?
No.
Okay, just look at this circuit. What do you think is the voltage drop across that bulb? What's the voltage drop? Whatever the voltage is, right? The whole thing drops. There's your closed circuit. But now look at this. Are these two resistors in series or not? Is that in series with that?
Someone said yes.
Who says yes?
I don't know. I just heard a yes. Tamika said yes.
Tamika, thank you. Tamika, explain to the rest of the class why that one is definitely in series with that. We can ignore the voltmeter. It's just a measuring instrument. Isn't it obvious that that is in series with that?
It's only obvious to Tamika, sir.
Okay, Tamika, can everybody see that that's in series with that? The current's going to go like this. It's going to flow first through this bulb, then through that bulb, and then it's going to come back. And okay, now let's ask if you agree that these are in series. Resistors in series are voltage dividers. Let's suppose the voltage is 6 volts. And let's suppose the bulbs are equal. What is the voltage drop across each of those?
3.
Exactly. So V2 is going to measure 3 volts. V1, which is the drop across that one, is going to measure 6 volts. So now, is the reading on V1 is half that of V2? No, V2 is half that of V1. Equal to that? No, twice that of V2. Is V1 twice that of V2?
Yes.
There we go. Mustafa, just ask them if they all understand that.
Only Azra understands. The rest of the class isn't answering.
Okay, ask them if there's anything they want me to explain again.
Jared says everything, sir.
Who says?
Cow, sir.
Okay, look. You know what I want you guys to do? Carry your crayons into the exam and color all the places that have no resistance the same color. What voltage is that purple or blue color? What voltage does that represent? 6 volts. Then get a different color and color from the other side all the things that are the same. You're not hitting a resistance. This browny gooey color, what voltage is this? Who can tell me what the voltage of this is?
Azra says 3.
Yeah, the one on top is the 6, so the one on the bottom is the?
Azra says 3.
But look, the bottom of the battery is always what? How many volts?
0.
Yeah. It always, the bottom of the negative side of the battery is always 0. The positive side of the battery is whatever the battery is. So all this brown, if it's brown, is 0, 0, 0, 0, 0, 0, 0, 0. So what is the difference in voltage between the blue and the brown?
6.
But blue and brown, what's the difference in voltage?
6.
So it's obvious that this voltmeter is blue, brown. So this voltmeter is going to measure the same as the battery, 6 volts. Okay. So now this is, we can see this, the current now comes to this bulb, then it changes color to this kind of sick looking color. And that sick looking color represents the voltage divided. So all the sick looking color is going to be 3 volts. So it's divided it half here, half here. So it's going to drop to 3 volts, 3, 3, drop again to 0. So resistors in series are voltage dividers. So there's 2 resistors. 6 divided by 2 is 3. All happy? Happier?
Yes.
Okay, let's go to the next one. The diagram below shows a cell of EMF theta or epsilon and 2 resistors R1 and R2 in series with R1 less than R2. Okay, R1's less than R2. The cell has negligible internal resistance and the voltmeters have very high resistances. Which one of the following is correct? Okay, so this one is small, that one is big. So which one's voltage drop is going to be biggest? Ask Azra. I think she answered that correctly before. Or it may have been somebody else. The bigger the resistor, the bigger the?
The bigger the voltage, she says.
The bigger the voltage drop when they're in series. So I know V2 is going to be greater than V1. Let's see if there's any answer like that. V2 is less than that, equal to no, okay. So V2 greater than V1. What the heck is this?
There's no answer like that, sir.
This looks like a power formula. Okay, it's a power formula. This one is volts upon resistance is current. Okay, let's try this one. Is the current through this one, volts upon resistance according to Ohm's law is current. Will the current through both of them be the same?
No.
We know the voltage is different. Will the current be the same?
No.
They're in series, right? Okay, but here is the trick. Do you know that the current everywhere in series is the same? Nothing can flow unless all flow. It's like water. The current can't dam up here. So the answer is actually C, that the currents are both the same, because V upon R is actually current. So volts upon resistance is current. The current through this one is the same as the current through that one. Okay, I'm going to just stop presenting for a moment because I can see that there's a confusion. Where, how can I represent it? I wish I had a necklace of beads. Okay, imagine this was a necklace of beads. If this bead moves, all the beads have to move. That's what current is like. It's like if this part of the river flows, that part of the river flows. All parts of the river flow at the same rate. So if I had a necklace of beads and I move the necklace, I pull them, they all have to flow or none flows. Tell me, does that make sense at all?
Yes.
So please write that down. For anything in series, the current through everything in series is the same. Okay, so let's try the next question. Okay, this one I've done at some stage or other in the past. Let's just see what the answer was. D. I forget who I did it with. Okay. Here, the minimum value of the resistance that can be obtained by connecting two 4-ohm resistors is. Okay, Mustafa, ask the class, what are the two possible ways we could combine those 4-ohm resistors?
In parallel and series.
Okay, so Mustafa, ask the class, or class, won't you work out what the total resistance would be if they were in series? And what would be the total resistance if they were in parallel?
In parallel, it's 2, so
And in series?
right.
So which is the minimum resistance?
B.
B. Okay. Nice one. I've done 1.58 with somebody. The answer is D. I can't remember who I did it with. I don't know if it was you guys. If it wasn't you guys, I don't know who it might have been, but anyway, 1.58 is D. Okay, yeah. 1.68. Learners investigate the relationship between the voltage and the current and the potential difference at a constant temperature for 3 different resistors, X, Y, and Z. They obtain these ohmic resistor graphs. Look, they put the volts on the top and the current on the up, okay? Which of these is getting the most current? X, Y, or Z? Which one's getting the most current, X, Y, or Z?
X.
X is the biggest. So is it the biggest or the smallest resistance? So it's the greatest I means the smallest or the greatest resistance?
Greatest. Greatest.
But don't resistors resist? This is just resistors done separately in a circuit. These are resistors by themselves. If you got a big current, you got a small resistance. I said if they're in parallel, but these are separate experiments. X has got the biggest current, therefore it must have the smallest resistance if it's just one resistor by itself. Does that make sense?
Yes.
And if you're needing me to go back to the Ohm's law thingy, the bigger the resistance, the smaller the current. The smaller the resistance, the greater the current. It's this circuit. One resistor, we crank up, I guess you're cranking up the voltage, but you're trying it with different resistors. And then you're taking your measurements. Okay. But it's just one resistor and different voltages. So, which one of the following conclusions regarding the resistors is correct? Okay, we know that X is the smallest resistance. Is X smaller than Y and Z? Is resistor X smaller than resistor Y and Z?
Yes.
So that must be correct. They're certainly not equal. Resistor X is not greater than Y, and resistor X is not greater than Y. Okay. Mustafa just asked them if they can see why this has to be so.
Yes, they can see.
Okay, great. As long as they can see it and remember it and work it out for themselves when they get exactly the same question. In the circuit diagram below, the resistance of resistor R1 is twice the resistance of R2. Okay, so let's draw it nice and big. It's twice as big. Okay, Mustafa asked them, where is the voltage going to fall the most of two resistors in series? Is it going to be resistor 1 or resistor 2? The bigger the resistor of resistors in series of voltage dividers, the bigger the resistance, the bigger or smaller the voltage drop?
Bigger.
Bigger. So we know that V1 is going to be greater than V2. Okay, let's just see. V1's equal to, no, V1's equal to half, no. V1's, okay, V1 is greater than V2. And they twice. So if there's twice, if this one is twice the resistance, it should be twice the voltage, shouldn't it? So which of these answers shows V1 is twice V2? Looks like it's B. Because so it must be B. V1 equals, oh, no, that's a half, eh? 2 V1 equals V2.
So
No. Which of these says that V2 is greater than V1?
Answer it's A.
V1 equals 2. Yeah, okay, that's a complicated way of saying that V1 is equal to twice V2. Yeah, okay, that's correct. A is the way of saying it. Sorry. Thanks. Ezra. V1 is twice V2. A certain conductor obeys Ohm's law. Which one of the statements below regarding the resistance of the conductor is correct? The resistance of this conductor changes as the potential difference across it changes. Does the resistance change in an ohmic conductor? No, the resistance should be constant. Changes as the current passing through it changes at constant temperature. No, the resistance doesn't change. Remains unchanged even if the potential difference across it at constant temperature. That looks correct. So in an ohmic resistor, the resistance stays the same, but the voltage increases and then the current increases. Remains unchanged even if the temperature changes. That's wrong. Temperature can change. The greater the temperature, the greater the resistance. So that's why this one is incorrect. Resistors, as they get hotter, they increase their temperature. So the resistance changes even if the potential different or the current in it changes at a constant temperature. Notice all the rest of them have constant temperature. And that is how we do the experiment. So the resistance stays the same, 1.88. I think that's easy enough. Just remember it. When a resistor of a resistance is connected to a battery of EMF E and negligible internal resistance, the power dissipated in the resistor is P. If the resistor is replaced with a resistor of twice the resistance without changing the battery, the power dissipated will be. Okay, so here's the circuit. We got a battery and it's got a resistance. That's all it is. Okay, there's very rough circuit. So now, if the resistor is replaced with a bigger one, what will happen to, so we put a bigger resistor here. What will happen to the power? Okay, now power is volts times amps. Okay, just remember that. Power equals volts times amps. Now, what will happen to the voltage? Will the voltage across the resistors change? Does the voltage stay the same or does it change?
Stay the same.
Okay, because you got the brown and the blue, okay? And then you're just changing the resistor. So if you, however, make the resistance bigger, will more or less current flow?
Less.
Will more or less current flow?
Less.
Less. So if power equals volts times amps, and if you increase the resistance, you get less amps, same volts, so therefore your power is going to become half. So here's the answer. If you replace it with double the resistance, you get half the power. Because you got half the current. Does that make sense? And if you take out the resistor and you create a short circuit, you're going to get sparks flying. That you can never get more power than if you just take the resistor out completely. You'll just get sparks. You never get more power than a short circuit. Don't try that at home, folks. Okay, 1108. 4 identical light bulbs. 4 identical light bulbs, P, Q, R, and S, are connected to a cell in a circuit, as shown below. The cell has negligible internal resistance. Which one of the following statements about the brightness of bulbs P, Q, R, and S is correct? Okay. So who can tell me which 2 bulbs will have the same current? Will S and Q have the same current?
Yeah. Yes.
Ask them how they know that.
It's in parallel.
They're in parallel, and therefore, if we have to color them in, they have the same color on either side of both of them. So these two going to have the same. Oh, that looks the same color. Okay, well, let's just try. So, oh, come on. Anyway, those two have the same voltage on either side. So the current is the same through both of those. Will those two have the same brightness?
No.
Remember, the same current that goes out of the battery equals the same current coming into the battery. So P and R will have the same brightness. For the same reason as I said, if you have X current going out, you have X current coming back. Current cannot get bottled up in one of those bulbs. Current is like water. It has to flow. Ask if that makes sense, please.
It makes sense.
Because they're in series. Anything in those two are in series. Forget all of that there. Now here's the question. What will, if this current is X and that current is X, what is this current here between these two? It's divided into two. So what is the current through S and Q going to be? Half.
Half.
Well done. So if you've got half current, do you think you've got half the brightness?
Yes.
Yeah, because power depends on current. So I now know P and R are the same brightness, S and Q are half the brightness. So let's just see. P burns brighter than R. No. S and Q burn brighter than P and R. S and Q, no. P and R burn brighter than S and Q. Yes, so that must be the answer. Okay, in the circuit below, the battery with an EMF that, an internal resistance that, with switch open, readings are registered on the ammeter and voltmeter. Switch S is now closed. How do the readings on the ammeter and the voltmeter change? Okay, don't look at that for a moment. Just look at this. Ignore the meters. If a switch is open, is this part of the circuit, can we ignore this part of the circuit? Just ask the Mustafa, if that switch is open, can we ignore R?
Can we? They say yes.
Do they all agree? We can ignore R. Okay, now
Yes.
now we close switch R, switch S. Now we've got two resistors in parallel. Mustafa, unless we have the memory of a goldfish, people are going to give me the correct answer this time. Will the total resistance decrease or increase if I have resistors in parallel? Will the total resistance of the circuit increase or decrease?
Decrease.
Sorry?
Decrease.
Well done. Resistors in parallel decrease total resistance. Okay, so what do I know? I know this ammeter is going to go up when this switch is closed. I know the voltage is going to maybe change. But what do I do? What I definitely do know is this current is going to increase when that switch is closed. Okay, so now let's have a look at the question. Switch S is now closed. How do the readings on the ammeter and the voltmeter change? Okay, when that closes, that current goes up. So I'm looking for ammeter goes up. So it's either A or B. Now let's have a look at the voltmeter reading. Will that stay the same? You're not going to get this, so let me give you the answer. If the current increases, what will the voltage drop across this do? Remember, voltage drop across little r. The voltage drop across little r, according to Ohm's law, volts equals I upon little r. But if the current has gone up, what happens to the voltage drop across little r? Anyone got an answer? If I goes up, which it has, what happens to the voltage across little r? The voltage drop.
According to Azra, it decreases.
Watch this. If I doubles, V doubles, because they're directly proportional. So the voltage drop across R is increasing. And that is what we call the lost volts. So as the lost volts increases, your voltmeter is going to register a lower voltage because more volts are lost inside as the current goes up. So I know my voltmeter is going to decrease. And so the answer's got to be decreases. Okay, this is a difficult question. If I had to ask them what do they or don't they understand, let's just start again. If that switch is closed, will that current increase?
Yes.
Okay, current increases. So the current everywhere is increasing, including through little r. Now we go to Ohm's law. Voltage drop across little r is equal to the current through little r divided by the resistance of little r. Is the resistance of little r changing?
No.
No. But the I has gone up. So if the I increases, the voltage drop increases. So say this was a 12-volt battery and it drops 2 volts here instead of 1, then this voltmeter is going to read a lower reading. Because of the EMF, which is, let's say it's 12 volts. And it was dropping here 1 volt. This was measuring 11 volts.
5 minutes the bell will go. It will be break time then. Educators on duty, please go out. Thank you.
But now, because the current's gone up, the voltage has now become 2 volts that it's dropping. So now this is 12 minus 2, which is now 10 volts.
Sir,
Okay.
go out.
There we go. Okay, guys, I'm finished here. Let me just get back to you. Have a good weekend, everybody. Thanks. I hope you learned something. I hope you're all going to become robotics engineers. I hope I inspired you.
I'm not agent, sir.
Anyone here interested in going into electronics?
No,
I happen to think Matsadisos may be interested in what they call
Mechatronics.
what's it called? Mechatronics. They got a fantastic section at UCT that I was going to take you to in April. The mechatronics department, which is a combination of motors and electronics, robotics. Okay, one of these days you're going to come onto my channel. It's going to be a robot sitting here teaching you. That's my dream.